Okay, in most cases, the population is so large that it's not feasible to study all the objects or items in the population. For example, it would not be possible for the quality control department of an automobile tire factory to check every tire to determine whether it will last more than 60,000 miles. What can we do? As introduced in the last chapter, an alternative to measuring the entire population is to take a sample from the population. And then we can test the statement to determine whether the sample does or does not support the statement concerning the population. Here, the statement or assumption about a population parameter, such as a population mean, is called a hypothesis. And the procedure based on the sample evidence and the probability theory we used to test this statement or hypothesis is called hypothesis testing. For example, we state the mean or the average data use for smartphone users is population mean is 1.8 gigabytes per month. That is a hypothesis. And then we take a sample and we follow the certain steps to test on this statement is called hypothesis testing. Usually we take the 5 steps to do the hypothesis testing. The first step is make statement. It's also make the hypothesis. Every hypothesis test has both a non-hypothesis and an alternative hypothesis. Non-hypothesis represents a status quo, and alternative hypothesis represents the opposite of the non-hypothesis. Non-hypothesis states a belief that a population parameter is less than and equal or greater than and equal or specific value. Remember, equal sign is always part of the non-hypothesis. And alternative hypothesis always states that a population parameter is greater than, not equal or less than a specific value. Remember, non-hypothesis and alternative hypothesis are mutually exclusive. What does that mean? Means if the sum in the non-hypothesis is less than and equal, then the sum in the alternative hypothesis is going to be greater than. If the not equal sum in the alternative hypothesis and then equal sum is in the non-hypothesis. If less than is in the alternative hypothesis and greater than and equal in the non-hypothesis, they are mutually exclusive. The purpose of hypothesis statements is to draw a conclusion about an unknown population parameter. Okay. So in the non-hypothesis, we state the unknown parameter has not changed from a status quo. And in alternate hypothesis, we say there has been a change in the desired direction. What does that mean? Let's check an example. The example is still about the average data use of a smartphone users. Okay, so if the statement is like this, in the non-hypothesis, it says the population mean, the average data use is less than and equal to 1.8. In the alternative hypothesis, it says the population mean is greater than 1.8. This test would be used by someone who thinks that the data use has gone up and wants to support that the average data use is now more than 1.8 gigabytes per month. If the statement is like this. In the non-hypothesis, it says population mean now greater than or equal to 1.8, and in the alternative hypothesis, it says population mean is less than 1.8. This statement would be used by someone who wants to test assumption that the data use has gone down. Okay, has gone down. If the statement is like this, in the non-hypothesis it's equal sum. Population mean is 1.8. In the alternative hypothesis, it says the population mean is not 1.8. This test would be used by someone who has no specific expectations. It's just want to test if there is a difference. Okay, if there is a difference from the 1.8. Let's go further. Okay, the sum in the statement are very important. It's gonna decide what kind of hypothesis testing it will be. So if the sum in the statement is like this, in the non-hypothesis the sum is equal. In the alternative hypothesis the sum is not equal, we're gonna use a two-tailed hypothesis test. Check this graph. Okay, so this graph gonna be divided into the three parts. There are two tails here. So if the statement is like this, we're gonna have two tails. That is the sample mean. We're gonna take a sample, right? So if the sample mean is followed into these two tails, in the middle is the population mean 1.8. So if the sample mean is much higher or much lower than 1.8, it's gonna be in the two tails, and then we're gonna reject the non-hypothesis. That means mu is not 1.8. If the sum in the statement is like this, it's in the alternative hypothesis, the sum is greater than or the sum is less than, then we're going to use a one-tail hypothesis test. If in the non-hypothesis the sum is less than and equal, in the alternative hypothesis the sum is greater than, then we're going to use the upper tail test. It's also called the right tail test. That means if the sample mean is much higher than the population mean, falling into this tail, and then we're gonna reject the non-hypothesis. If the sum look like this, in the non-hypothesis the sum is greater than or equal, and in the alternative hypothesis the sum is less than, and then we're gonna use a left tail. It's also lower tail test. That means if the sample mean is much lower than 1.8, then we're gonna reject the non-hypothesis. So sum in the statements are very important. It's gonna, help you determine what kind of the test we're gonna take. Two tails or one tail, left tail or right tail. Remember, the non-hypothesis can never be accepted. There are only two options available, are to reject the non-hypothesis or fail to reject the non-hypothesis. Okay, so the non-hypothesis is tested using sample data. The sample result provides enough evidence to reject the non-hypothesis or does not provide enough evidence to reject it. Another very important thing is type 1 error here, because we know sample evidence is not perfect, right, because of the sampling error. So a conclusion about the population might be wrong. Type 1 error occurs when the non-hypothesis is rejected when it is true. So the probability of making a type 1 error is known as alpha, the level of significance. So alpha, the level of significance, is the probability that we reject the non-hypothesis when it is true. In the graph, the yellow tails, the yellow area are alpha. Those represent the probability that we reject the null hypothesis when it is true. Remember, when we do hypothesis testing, we always decide on alpha first before we take a sample. Okay, now let's check the hypothesis testing for population mean when population standard deviation is known. Okay, we're gonna check the hypothesis testing, and we start with the example, and in this example we're gonna introduce you all the steps. We just done with introduce the step 1, make how to make a statement, right? And now we're gonna get to learn how to do finish the other steps in an example to do this hypothesis testing. Here we're gonna give you an example of a one-tail hypothesis test for a population mean when sigma, the population standard deviation, is known. Okay. Example: a new CFL bulb is claimed to have an average life that exceeds 8,000 hours. Suppose average life of a random sample of 36 of a new bulbs is 8,120 hours. Assume the population standard deviation for the life of this kind of bulbs is 500 hours. So we're gonna make a statement about the population mean, which is average life exceeds the 8,000 hours. Okay, the lifespan is 8,000 hours, and we take the sample 36 samples, and we found out the sample mean is 8,120. Sample mean is greater than the population mean, so we want to know if the population mean now is more than 8,000 hours. Step 1, make a statement. Identify the non and alternative hypothesis. So remember, you need to write out the complete statement, right? The non-hypothesis we write as H sub 0, right, is mu, population mean, less than equal to 8,000 hours. And the alternative hypothesis, H1, is mu greater than 8,000 hours. Remember, equal sign is always part of the non-hypothesis. And in the alternative hypothesis, we want to know if the new bulb lasts longer than 8,000 hours. In the non-hypothesis, it states a status quo, right? Average life is not greater than 8,000 hours. Step 2. Step 2 is actually always be together with step 3. Step 2 is a set of value for a significant level alpha. Okay. Usually this value in the questions, this value is given, right? So here, suppose that alpha is 0.05. 0.05, that means we're gonna assume the probability that we reject the non-hypothesis when non-hypothesis is correct, is right, is 5%. Step 3. Step 3 is actually the continuum of the step 2, because the step 3 we're going to determine the critical value. Critical value is decided by the alpha. Critical value is decided by the level of the significance. Okay, remember I told you the alpha in the graph is this area, right? Alpha is this area. So alpha represents the probability that we reject the HO when it is true. So critical value is the Z value. In this case, okay, in this one-tail hypothesis test for population mean case, the critical value is the Z value for this point. For this point, you see my mouse here is for this point. Okay. So critical value is the value divide the distribution, the whole distribution, into the two parts. One part we call that acceptance region. The other part we call that rejection region. So this area equal to the alpha, and the point, the z value for this point, we call that critical value. So in order to find out the critical value, we need to know alpha. So by using the alpha and look up the z table, we can find out the z value or z score for this point. Okay, I'm gonna repeat this because this is very important, right? Our sigma is known, so use a z-score. Right? Sigma is known, so we use a z-score, z-distribution. When the sigma population standard deviation is unknown, we're gonna use a different, okay, not z-score, we're gonna use a different distribution. But here, in this class, I'm gonna just use the case of the sigma is known. So for sigma is known, we're gonna use a z-score. The critical value is a critical z-score identifies the rejection region for this one-tailed test. Since this is a one-tailed test, the entire area for alpha equal to 0.05 is placed on the right side upper tail of the sampling distribution. Remember, when your sign in a statement like this, in the non-hypothesis, the sign is less than and equal. In alternative hypothesis, is greater than. In the previous slides, we say it's upper tail, right? It's right tail. So this area is alpha. Okay, because we know alpha is 0.05, this area, so that means this area, this whole blank area is 1 minus 0.05. We get a 0.95, right? We get a 0.95. By looking up the z table, you will find out the z value for this point corresponding to the probability of the 0.95 is 1.645. Is 1.4645. Okay, so step 4 is compute the test statistic. So for step 4, we're gonna find out the z value for the sample mean. Okay, we're gonna find the z score for the sample mean by following this formula. Okay, so the z-score for the sample mean is sample mean minus population mean, or the mean in the statement, divided by the standard deviation of the sample. Remember, the standard deviation of the sample equal to the population standard deviation divided by the square root of the n, the sample size. Okay, so plug in all the numbers into this formula. So the sample mean is 8,120 and the population mean is 8,000, right? So sample mean minus population mean divided by the standard deviation of the sample, that is 500 over square root of 36. We get the result is 1.44. This 1.44 is a z-score for sample mean. Step 5 is gonna be, we're gonna compare the z value of the critical value, which is decided by the alpha, right? And the z value for the sample mean. Sample mean we get is 1.44, right? So the critical value is 1.64 and the sample mean, the z value, z-score for sample mean is 1.44. So 1.44 is less than the critical value 1.64. It is not in the region of rejection. The sample mean follow into the area here, okay, follow into the do not reject HO area. So that is actually the next step. Next step is compare the z-test statistic z-value, right? Z-value for sample mean with a critical z-score, with a critical value. For one tail upper tail test, reject non-hypothesis if the z-score for sample mean is greater than the critical value. However, here 1.44 is not greater than 1.65, so do not reject non-hypothesis. See, the test statistic, the z-value for sample mean is 1.44 is less than the critical value 1.64, so we do not reject non-hypothesis. So last step, state a conclusion. We're going to draw a conclusion. So based on our testing, based on our sample evidence and the probability theory, we got a conclusion here. According to our sample of the 36 new bulbs, there is not enough evidence to support the claim. What kind of claim? That average life of those bulbs exceeds 8,000 hours. So even though the sample mean, the sample mean is greater than 8,000 hours, but we cannot claim that the whole population mean is exceeding 8,000 hours. So we just covered the case of this one, the one tail upper tail test, right? So for this kind of test, the hypothesis statements like this, then here are the decision rule. Okay, we call this the decision rule. Then that's the conclusion. Okay. There are another two cases. Okay, there are other two situations. One is a two-tail test. In the two-tail test, the statement gonna be in the non-hypothesis, the population mean, we make statement of population mean equal to a specific value. In the alternative hypothesis, population mean is not equal to that specific value, right? And the condition gonna be because this is two tails, right? So hold on, let me show you the picture, right? Say these are the situation of the two tails. So the alpha, these two areas together is alpha. So this part is alpha divided by 2. This part is alpha divided by 2. And these two areas are gonna decide the critical value is z value for this point and z value for this point, right? Z value for this point. And then we're gonna calculate the z value for the sample mean. Once we get the z value for sample mean, we can use that z value for sample mean compare with these two critical values. If the z value for sample mean is less than this critical value or greater than this critical value, we can reject the non-hypothesis. Or, if the z value for the sample mean is greater than this critical value and less than this critical value, and then we will not reject the non-hypothesis. Say it's the decision rule is written here. Okay, pay attention here, the critical value alpha divided by 2. Okay, critical alpha divided by 2. And the third situation is one tail, the left tail, right, the lower tail, when your hypothesis is like this. In the non-hypothesis mean greater than or equal to a specific value, and in the alternative hypothesis, the population mean less than a specific value, and then we're gonna compare the z-value for the sample mean and the z-value for the critical value. That point we're gonna compare that two values. Let me show you. Hold on. See, here is for the lower tail test. So we find out the critical value for this point, the z-value for this point. We find that by looking up the z-table, and we know the area of this yellow area. This yellow area is alpha, the level of significance, and then we compute the test statistic, that is the z-value for sample mean. Then compare the sample mean with this critical value. If sample mean greater than this critical value, we do not reject null hypothesis. If the z-value for sample mean less than the critical value fall into this rejection region, then we reject the null hypothesis. Okay, now you need to do a lot of exercise to practice and be familiar with those steps, right? The first step, make a statement, and the second step, identify the level of significance. The third step is find out the critical value based on the alpha level of significance. The step 4 is compute the test statistic, that is find out the z-value for sample mean. And then the fifth step is gonna compare the z-value for sample mean and the z-value, the critical value. And last step, you're gonna draw your conclusion. Okay, draw your conclusion based on this table. Okay, so let me know if you have any questions. Thank you.